Hi, students of chemistry. I wanted to go over some significant figure exercises and lessons with you. I'm going to try to make this video brief, although it is an in-depth subject and would take some time for a thorough understanding, but this is more of a polishing lesson. So the things we're going to go over today are the rules for determining significant figures, and I'll talk a little bit about what are significant figures exactly. We're going to talk about, once you know how many significant figures there are, you've determined them, how many are there left over in a calculation, how to handle calculations. Since it's closely related, we're going to talk about scientific notation. We're going to talk about calculation of quantities. Scientific notation is kind of like the number 2 here, but for scientific notation. And then we're going to talk about entering significant figures in a computer, and more specifically in your homework, which is Webassign, your homework website, or something like a spreadsheet, how to take care of significant figures and scientific notation. So exactly what is a significant figure? What does it mean, and how do we use it? Well, a significant figure is a way of performing error analysis. Now, error analysis, there are many ways of performing error analysis, and the simplest one is significant figures. And we say significant figures. So that is a count of the number of digits reported that we know to have been measured exactly. And so that you may report more digits, or you may have a chance to see more digits than are reported exactly, or fewer. The worst case is, who knows whether the worst case is reporting more than you're justified in, or reporting fewer. So, for example, a lever balance, that may be used to weigh a truckload of rocks, may be accurate to the nearest 100 kilogram mark. Let's say it's weighing out plus or minus 100 kilograms. Let's say you had a reading of 15,200 kilograms. For example, the measurement should be written in such a way to communicate this to someone else that the person reading it will understand that it represents the mass of this truck to the nearest plus or minus 100 kilogram, or this particular point here. That is, that the mass here you're reporting is actually somewhere between 15,100 and 15,300 kilograms. That the error is in this point, and we don't know these digits very well at all. Whenever you report significant figures, you always report all the digits that you know for sure. This one's going to be for sure. One number you kinda know. And then any others past that, or there's no possible way that you know these numbers. And so this unit represented here, 15,200, we would say in this case has 3 significant figures. Has 3 significant figures. I'm just going to start writing SF in the near future. So this has 3 significant figures. Only 1, 2, 3. And I'll give you some lessons on how to count those in a moment, but let's talk about them a little more first for a second. So to convey the accuracy of measurements, all people working in science anyway use significant figures, even though there are other methods of error analysis out there. And the significant figure is a digit that represents an actual measurement. Let me write this down. Here, go back to this again. An actual measurement. I'll write this a little neater than I did my last slide. So we said just a moment ago, that the mass of the truck was 15,200 kilograms. That's just something that I just made up. So the 1, the 5, and the 2, we said, are all significant figures. 1, the 5, and the 2 are all significant figures. So the question is kind of what are the zeros then? And so we said that the truck was not sensitive enough to give us data that's reliable out to the tens place in the single digits place, because this is the ones, the tens, the hundreds, the thousands, and the 10,000s place. Therefore, the 2 zeros reported here are not significant, and that's important to note, that these are not, they're what we call insignificant or not significant. Not significant. So this number has 3 significant figures. If we did something else, if we had a piece of aluminum foil, for example, and we said that we had 0.206 grams, for example, making this up again, this one also has 3 significant figures in it. And we need to communicate these values in such a way that people seeing the numbers that we write down understand. Like this one would be pretty easy. You would understand that this, you know, this one to three digits here. There would be this many places. But if you were to put, what if I wrote this number here? What if I wrote 2060 grams? It's the same number, but I know it to not just the 1, the 10, the 1,000, but the 10,000th of a gram place. It's telling the reader something else. For someone seeing this understands the precision of this number. And so we'll go over how to communicate, how to read the numbers. If we see a number, how to read how many significant figures are in it, and how to report how many significant figures we're going to give to somebody else. So now I'm going to talk about the rules for determining significant figures. So the first rule is that all, oops, sorry, let me get over here, change colors for you, so that all non-zero numbers are significant. And I guess since I have a typewriter here, I'll just maybe type this out too. I'll say that all non-zero numbers are significant. So some examples, please. Here we go. We'll give you some examples. So if you had, like, for example, the number, if you were reporting 325 milliliters of ethanol, this would have 3 significant figures because there's 1, there's 2, and there's 3. If this number were 1.325 grams of zinc, you would have 1, 2, 3, 4 significant figures. I should have put 3 significant figures here because you have 4 integers or non-zero numbers. So anytime you see a number, and if you see a counting number and it's not 0, then it's always significant. It's never, that's hard and fast and never changes at all. But things aren't always that simple. So let's say that we have some zeros in a number. That would make it less simple. Zeros between non-zero digits are significant. So we'll have we'll call this number 2, and we'll say that zeros. Now we only have to worry about zeros from now on, because any integer, any counting number is definitely significant. Zeros appearing between non-zero digits are significant. So, for example, if it's sandwiched between 2 integers, it's always significant. So if we have, let's say, 4.07 liters of, I don't know, Kool-Aid. This many liters of Kool-Aid. This has 1, 2, 3, and the 0 is significant because it's between 2 integers. We have 3 significant figures. If you had 3,206, 32,006 feet of cable, you would have 1, 2, 3, 4, 5 significant figures. Pretty easy, right? Probably some of you are bored watching me go over this, but believe me, some people are not bored, so that's why we go over it. So we say 0. Another thing is that a 0 to the left, and we'll go this one here. We'll say a 0 to the left of an integer is not significant. A 0 to the left of a non-zero digit is not significant. So the number 0.0572 meters squared, this guy has, let's count them. How many significant figures are there? We've got 1, 2, 3 significant figures because the zeros to the left don't count. So, example, if we had 0.000, this is you reading someone else's number, right? Grams of, I don't know, DNA molecules or something. This would just have one significant figure if you're reading it. So, zeros at the end of the number and to the right of a decimal are significant figures. So if it's, we'll start another one here. I think I can probably just type right here on the same page. I'll just go down and I'll say that for zeros at the end of a number and to the right of a decimal place are significant. So for example, if I were to write the number, let's just write 97.00, what is that number here? What is that? Is that significant or not? Well, we just said that these guys are significant. So this one was going to have 4 significant figures. There's 4. I'll erase some of this so you can see it a little more clearly. I'll start over. This one has integers, so integers always significant. 1, 2, 3, 4. You have 4 significant figures. And if you have 1200.00, this one might be a little tricky, right? But these are to the right of an integer to the left of a decimal place, but these guys are sandwiched between 2 other significant numbers, so they automatically count as being significant. So we have 1, 2, 3, 4, 5, 6 significant figures. You read this number reported to you by a scientist, you know that it has 6 significant figures. And that seems pretty straightforward so far, but here comes the tricky part. The tricky part is that the zeros at the end of a number to the left of a decimal may or may not be significant. So if we see a number, like the number, let's read one here, 3,400 grams of sulfur, let's say, or let's say your friend owes you $10,000. We don't know if they owe you exactly $10,000. They might. Or if they owe you some amount of money close to $10,000. Is it exactly $10,000? Written like this, we don't know. We just can't tell. And so if they had the number 3,400 grams of, let's say, sulfur, written like this, we don't know if these 2 zeros are significant or not. It's just we're just a victim of the way people write down numbers. Now note that you only use significant figures, and this will help bring this home a little bit, I think. You only use significant figures when you are reading or reporting or working with measured quantities. Measured quantities. They have to have been something measured. So when do you not use significant figures? Never when using defined quantities. So you don't use them in things like conversion factors, because conversion factors are always defined. So if you say that there are 12 inches is equals to 1 foot, that is infinite precision that you know this because that is defined. You don't use it when you count things with count objects. So if I say you have five, I don't know, 5 shoes, and you counted how many shoes you have 5 shoes. So you can't use significant figures in that. So, and that's sort of an aside, but it's the best time to, I think, to bring it up, when to apply these things, is when you have this ambiguity over whether these things were counted or measured, or how do we have these zeros, what's going on. How do we report a number like this if we know the number of significant figures? Well, then we use scientific notation to do that. So if this were to the ones place, scientific notation has a number in the front. Let's just call this number A times 10 to the B. And this is the exponent here, and this is the number. This number, the decimal here, the number in this case is always between 1 and 10. And it's times 10 to the some other power. B is always an integer, a counting number. It can be a positive or negative whole number. Whole number. So, for example, if this number, 3,400 grams of sulfur, if it had one significant figure, if it has, let's just write this number of significant figures here. And I'm going to put the scientific notation. This is how we would communicate it here. If it has just one, we would round it, first of all, and then we would call it. If it were one significant figure, we would just say 3 times 10 to the 1, 2, 3 times 10 to the 3. We'd round that down to 3,000. If it had two significant figures, we would call it 3.4 times 10 to the third power. See, 3.4. If it had 3, if we were to report, so that meaning that it was, I'll show you what that means in a minute. So if it had 3 significant figures, we'd 3.40 times 10 to the third. And if we wanted to say it had 4, we'd say it's 3.400 times 10 to the third. So what's the distinction? Why would you report one number versus the other? So, well, you took this data, you're the one reporting it in the first place, so you have to communicate what the value is of your error in this number. So I'm just going to move this over to here. And what do these actually mean with respect to how much you're reporting? Well, this number here means somewhere between 2,000 and plus or minus 1 in this place here, so 2,000 and 4,000. So that's a broad range. This number here means somewhere between 3,300 and 3,500. This number means somewhere between 3,000 and what would round to 40 in this place, so it'd be 3,390, right? Because we're going one more place over. And this would be 3,410, 3,410, because both of those would round to 3.40, and then set and so on and so on. And so you're getting better and better precision. The next one would be 3,399, 3,401. So that's what these numbers represent. You have to communicate that to this other person. So in the case that you give a 0 to the left of a decimal, to the right of an integer, the best way to communicate that is with scientific notation. And I'll also show you how to do that in your calculator really quickly. And we'll have a whole section just on that in a little bit, but I wanted to show you just really quickly, because some of you are just wanting to learn that only right now. If you wanted to put 3,400 in your calculator, you can do that. If you wanted to report it, you'd say 3.400 second function double E, and you can follow my keystrokes here. I'll let you see my keystrokes. So I put 3.400 second function double E, key there, and then I put 3 and enter, and that means 3,400. If I put 3.400 and I want it to be minus 3, so that would represent a much smaller number, then I would not put 3400 minus. This would be a no. You'd put 3400. Sorry, I did it prematurely. 3.400 second function double E negative, not minus, negative 3, and that gives you a smaller version. If you tried 3.400 second function double E minus 3, it might still work on some calculators. Does not work in this one, but you need to put the one with the parentheses in it for the TI calculators. Also, you should note that many of the TI calculators have an app in there that's under apps. I clicked apps to get to this menu, and if you click down here, you go to the scientific tools. You can hit the number 9. I'm going down to the scientific tools. There's an app here, which I'll go up a little bit. I'm going to hit enter, and one of them is and this is exactly what your screen will look like. One is a sig fig calculator. So if we hit 1 or press enter there, we get a sig fig calculator. It also does the math on significant figures for you, and I do have a video on this later. So if you had the number 3400, enter, it tells you that there are 2 significant figures. Why does it say that? Because computers don't have the ambiguity in them that we do as humans to be able to say we don't know how many there are. Webassign will read them like this, just like your calculator does. If you write down 3400, it will count this as having 2 significant figures. If instead you wrote the number 3.400 second function double E to the 3rd power and then hit enter, it tells you you have 4 significant figures. What's great about this sig fig calculator too is that it actually keeps the number of significant figures for you if you have this. It's a great tool. So if I were to put 3.241, which has 4 significant figures in it, and I were to multiply that by let's say 2.2, which only has 2 significant figures, it would give me the answer and maintain 2 significant figures. It does the same thing with addition and subtraction, which has different rules, and we will go over that in a little bit. About doing measurements and doing calculations, with significant figures. The first rule is for multiplication and division operations. For multiplication and division, you want to keep the same number of significant figures as the term with the fewest significant figures. And in addition and subtraction, you want to round off to the fewest number of decimal places. You want to keep the term with the fewest decimal places. So I know it seems a little weird to you. There are good reasons for this. It may seem a little weird anyway. I don't know for a fact that it seems weird to you, but it is. And if you have different operations, you need to follow the rules of math and stop and multiply. Do all your multiplication first, evaluate your significant figures, then do your additions, etc., etc. And it's a little trickier than it might sound when they have multiple ones, but you have to stop and do it to get the right answer, to report the right value to someone else. So, for example, if we had a number in which we said that we wanted density, we said density hay is equal to mass over volume, and we had a problem in which we had to divide 11,000 and let's say 79 grams over 12.7 milliliters. Then our calculator spit out the following value, 0.8, let's see, 72362 204 grams per milliliter. What do you report? This is a huge number. What do you actually give other people? Well, this term has 3 significant figures. This one has 3. This one has 1, 2, 3, 4, 5. 5. So we round off to 3 in the answer. So this is insignificant. So we round it off to 1, 2, 3. So we report just 872 grams per milliliter. And this was 872.3. The next number was 3 in our series here. If this number were 6, we would kick this up 1 to 873. That's what you would report. And you might even write it in scientific notation. In that case, this number is not between 1 and 10, so you would say 8.72 times 10 to the minus 1. And For an addition and subtraction, for addition and subtraction, you would say, let's say the same two numbers. If we were to take 11.079 and 12.7, and we were to add them, well, we would go 977.23.779, but we could only keep as many decimal places as the term with the fewest decimal places, and so we would just report 23.7 in that particular case. And it seems simple and straightforward now, I know, but you have to keep track of these guys. So I'm going to spend another moment here. I wanted to keep this briefer than I had been, but I want to prove this to you. I want to show you that this really means something that's true and it's meaningful. So what I'm going to do is I'm going to take an example, and I'll type this so you can read it a little better. Whoops, I got a little mess here. So I'm going to write down some math. I'm going to say we had three measurements. Let's say we had, I don't know, 132 times 13 times 14. And what does this, no, let's make this other number bigger. Let's say 155, let's say 155. So what does this mean? Let's look at which of these three terms has the fewest number of significant figures. Well, it's this one here. This has 2, this has 3, this has 3. And I say that the term with the fewest significant figures controls the error in the answer. So let's do a little experiment. What does 12 times 13 times 155 equal? Well, let's find out. Let's go to our handy calculator over here, and let's put in, let me click this up here again. So let's clear from our last problem. We have to second function quit, and we're going to go with exit here. So we're going to hit exit, and what do we say again? 12 times 132, so 132 times, 13 times 155. Whoops. So it's 26,190. It doesn't sound right. Oh, it's not. 132 times 13 times 155. There we go. Why is it not putting 132 times, I have a solar powered keyboard and it's late at night now, times 155. There we go, 265,980. So let's write that over here. So we'll write down 265,980. It's 265,980 is our number. Now that is the with 13, but 13, remember, means all the numbers between 12 and 14. Right? Let's write them all down here. So we have all the numbers between 12. It means everything between 12 and 14. That's the one with the fewest significant figures. So we said 265,980. Is that right? Is that what we? 265,980. Yep, it is. So 265,980. So let's do this with a 12 instead. So let's do 132 times 12 times 155. So I'm going to do that right now. I'm going to say 132 times 12 times 155. What? 132 times, this keyboard does not like my 2's. 132 times 12 times 155 is 245,520. So let's write that up here. 245,520. 245,520. And if we did 132 times 14 times 155, so we did, let's say 132 times 14 times 155, and we get 286,440. 286,440. 286,440. So what is the take-home message here? Let's look at these numbers and where do they first the error show up in this answer. If we were to report 265,980, and let's say we're going to do that, 265,980. We follow the rules. We'll say that we're only going to report two significant figures. That means that we know one for sure and one kinda, right? And we would report this as 1, 2, 3, 4, 5. We would say it. We would report this as 2.6 or 7. These rounding rules would say 7. I'll say 2.6 times 10 to the 1, 2, 3, 4, 5, 10 to the fifth. And the reason I said 6 is because the real rounding rules are round to even number to split the odds of you accidentally rounding too high or too low, 50-50. But your middle school rounding will tell you 5 and above goes to 7, and that's what we do in this class too, but my instincts won't let me do that. But so we report this number, and we actually are reporting a number somewhere between 2.5 times 10 to the 5 and 2.7 times 10 to the 5. We're saying the real number is somewhere in there. Now what happens really is if this number were all the way down as far as 12, we'd get 2.4 and we get 2.8 on the high end. So the error, where does the error show up? Does it show up here? This first number? Nope. They're all the same in all these cases. What about the second number? Does it show up here? It sure does. And these ones are completely bad. These ones wiggle a little. These ones are gone. So this is why we report one number we know for sure, and one that the error is likely to creep up in, which is the second one. But let's say that this number were defined, and we were changing the 155 number instead. Where does that number show up at? So let's say the 155 has error in it, but that the 13 is a defined value. So if we start off at 265,980, and we just change the 155, so 132 times 13 times 156, so 132 times 13 times 156, now where does the error show up? 267,696. So it shows up over here, 267. Let's put the 156 below, 156, and it's 267,696. And if it were 154, it shows up, well, let's see where. Probably the same place, I'm guessing. So 132 times 13 times 154, and 264 is the answer to 2. So it's 264. So now we have a for sure and a for sure and a kinda. So this is what we report. Now we report 2.65 times 10 to the fifth, because now we're saying that this number is somewhere between 2.64 and 2.66 is what we're claiming. And if you wiggle this last number here a little bit, here, if you say the error is here limited, then you get your first wiggle there. So this is proof to you that significant figures matter, and what we're doing in reporting is really the math bears it out. We are sending data to other people that we believe, and have propagated that error through the math. Hello, I'm just going to do a few examples of scientific notation here, because I believe you're probably pretty good at this and you can let your calculator handle much of it, but I want to go over it a little bit just in case. Scientific notation is just a way for us to handle really large or really small numbers, and it is always written as follows. And I gave a few different variables earlier, but I'll just vary this a little. I'm going to say that it's written in the form of a coefficient or a decimal equivalent, whatever you want to call it. Let's call this number, I don't know, m or a or whatever you want to call it. And it's multiplied by an exponent, which is 10 to some other value. And that helps us to express the magnitude of the number here. This is how big it is. Magnitude. And this is the precision of the number, how well we know this number. So this front part here, and I wrote m because it's actually called the mantissa, but we're going to call it just the coefficient or the decimal, whatever you want to call it. This one always carries all the significant figures. It has all the significance in it, and it's always between 1 and 10. This magnitude just tells us how big this bit of significance is it's always 10 to some whole number, 1, 2, 3, 4, 5, 6. It can also be plus or minus, and that's the framework that you have for this thing. And so I know that you already know some of the values that you're going to be writing. You know the decimal equivalents of some of these, and so just to express this a little bit, like 10 to the minus 2 is equal to 0.01 because it's 10. This 1 times 10 to the minus 2 is 1 times 10 to the minus 1, 2. 10 to the minus 1 is equal to 0.1. 10 to the 0 is equal to 1, because anything to the 0th power is equal to 1. 10 to the first is equal to 10, and 10 to the second is equal to 100. Likewise, you should probably already know this, but any number, x to the 0, is equal to 1. If you take any two numbers and you multiply them, you get their exponents. So x times y times a, y to the 8th power times y to the bth power equals y to the a plus b. And likewise, y to the a divided by y to the b is equal to y to the a minus b. These are some basic math things, but I thought that might be a nice reminder. Some typical numbers we run into in chemistry. What are some things that we would want to use scientific notation for? So the density of air, what we call rho, the density of air is equal to 0.00161 grams per cubic centimeter. And in scientific notation, that is 1.61 times 10 to the minus 1, 2, 3, 10 to the minus 3 grams per cubic centimeter. And the radius of a calcium atom is 0.12345678997 meters. That's a calcium atom. That's how big across it is. It gets onerous to write that down all the time. So what is this number? This one in scientific notation is 1.97. How many is that? Times 10 to the minus 10 meters. A light year. What's a light year? A light year is distance that light travels in space in a vacuum in 1 year. And that is 9,460,000,000,000 kilometers. That's how far it travels in a year. That's a 0. And that number is 9.46 times 10 to the 12th kilometers. And the mass of a neutron, what is the mass of a neutron? This is just some practice for you. It's 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 0, 0, 0, 2, 3, 4. I got 2 more to go. 0, 0, 0, 0, 0, 0, 0, 0, 1, 6, 7, whoops, 6, I'll erase that, 675 grams. And so you would write that as 1.675 times 10 to the minus 24 grams, or, oops, 24 grams, this is supposed to be a 4, or 10 to the minus 27 kilograms. And those are just some examples of writing numbers in scientific notation, both large and small. Hi, so this section is going to talk a little bit about how to handle reading and reporting significant figures in scientific notation in your online homework, which is in Webassign, and in computers in general. Excel is very much the same way too, if you write spreadsheets. So one thing to note is that if you write, you wanted to write the number let's say for example 6.02 times 10 to the 23rd, and you want to write that in your computer, you would write it as follows. You would write 6.02 e to the positive 23. That's how you'd write it. So e means times 10 to the. So that's what you'd have to do. The other thing is, if you have, if you wanted to write just a single digit, you could write e to the plus 2, but sometimes in spreadsheets you might want to write e to the 0 too. For example, if you had the number, let's say 340, for example, let's say 340, you might want to write that as 3.40 times, which would be times 10 to the second power. You might want to write 3.40 e to the plus 02. And of course minus if it were 0.034. If you were to write 0.0340, that would be, you would rewrite that as 3.40 times 10 to the minus 2, or 3.40 e to the minus 2. And it's not 2, that's not a big minus 2. You'd write it like the 3.40 e minus 2 in the same line. This means times 10 to the. So don't put a times 10 to the in there. 3.0 times e to the minus 2. Don't do that. And don't put e to the minus 2. Don't do anything else. No other. Don't get creative. It's not time for creative formatting. Don't do that. That's how you enter. And I'll give you some examples in first your calculator and then in Webassign. So let's talk about entering these numbers in your calculator. This is stuff I see all the time in chemistry classes, all the way to the end of the quarter. Here is what you would do right. Let's say you would write 3.40 second function double E 2 to mean 340. Hit enter. Number 340 comes out. Check. You're good. Here's what happens all the time. A few mistakes. I already talked about using the negative versus the minus sign in the exponent. This is another one. You'd say 3.40, and then someone will put times second function double E minus 3, something like that. Enter. And that is the wrong number. You see that? Because if you just put e to the minus 3, it's times 1,000th. You see? And you would never know. It just comes out. And students get really creative putting different things in there, and it's not right. Also, what you don't want to do either is go 3.40. Some people will put 10, and then they'll put the carat sign, the power sign. They'll put times 10 to the third. Now, or second. Let's see what happens. I should have put 10 to the second here. Let's go back 10 to the second power. Now, what happens with this one? This is the right answer in this case, but it isn't always the case. In some calculators, what it does is it'll take 340 times 10, which would be 3.40 times 10, which is 34, and then square that number. So be aware that some calculators don't handle that very well. This particular one happens to, but many do not. And so be very, very aware of that. There are errors in entering it. Know your calculator. Make sure, do a few test problems. If you're not getting the right answer in Webassign, look for this error. But I recommend always you do something small. You would say 5.2 second function double E negative 6. Enter that. You put the negative and not the minus sign. And this one isn't. It's too small to report as a decimal. Let's go 5.2 second function double E negative 2. That ought to spit it out. There you go. And it tells you it's a smaller value there. Let's do a few. Let's look at some problems in Webassign. And first thing to note, if you see this little blue box right here in Webassign, this tells you the rules for reading and reporting significant figures in Webassign. So here we go. Every non-zero digit significant. Zeros between non-zero digits are significant. Zeros at the end. Blah 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 blah. just like we said. And this is exactly how Webassign reads them. Webassign reads this number here a little different than we say we don't know, but a computer, that's not a good enough answer for a computer. So the computer says if this sees the number 500, that's 1. If you see the number 13,000, that's 2, because these are considered insignificant in Webassign. You see 140 times 10 to the minus 001 times 10 to the first, it's 2 significant figures. There's 2 right there. That's 2. If, however, and this is what many computers do, it's different than the way we write, zeros at the end of an answer when there's a decimal point, they are significant. So 500, in contrast to having 1 here, if you put a little dot, that's how you tell the computer that these numbers written not in scientific notation are significant. 5.0, just like we do, it's writing scientific notation, times 10 to the second is 2. This is 4 because these zeros are to the right of the decimal. And this is 6 also because those are right of an integer and right of a decimal. So this helps you click that little button, and it also tells you that you're being graded on the number of significant figures. So this problem reads, how many picograms are in 3 milligrams? And the answer here is 3 times 10 to the 9th. Let's see if we can come up with that and then test ourselves here a little bit. So the question is, how many picograms in 3 milligrams? Well, let's write it out. So So when we write this out, here's what it looks like. We look at something like this. We say we have 3 milligrams, and we want to get to picograms. So how do we do that? We say, okay, well, we know that there are 1 times 10 to the minus 3 grams is a milligram, and we also know that there 1 times 10 to the minus 12 grams is a picogram. And you could also say that, conversely, you could also say that 1,000 milligrams equals 1 gram, and those things are both true. So one way to set this problem up is as I've written here. You could say, and I'll write this from scratch over here. You could say that you always write with what you have first. You have 3 milligrams, and what I like to do is go back to the base unit and from the base unit back out again. So I have 3 milligrams, and then I'll say, hey, and 1 milligram is how many grams? Instead of writing it like I did up here, I'm going to do a counter example for you to show you it's the same exact thing, but it'll give us more variety in how we enter this into the calculator. We'll say 1,000 milligrams is 1 gram. And we wrote milligrams on the bottom so that they can cancel. And all I did was go back to the base unit so I could go from one to the other, and it makes more sense to me this way. And then you can say that there are is that 1 gram, or how many grams are in a picogram. You would say that there are 1 times 10 to the minus 12 grams in 1 picogram. That's the definition. And then you would calculate this value and see what you get. Now Webassign says we should get the value of 3 times 10 to the ninth. So it says we should get 3 times 10 to the 9th power. And note that's only one significant figure, which is appropriate. So how would we do this in our calculator? So let's go back to our calculator. We'll clear this, and we'll just do right what it says. I'll see if I can get both of these on the screen at the same time. That might be nice for you, but I don't know if that's going to happen. So we'll do our best. We'll say, so what we're going to do though is, and I'll write it down here, maybe I can just fit this in here. We'll say we want to get, the math is going to be 3, it's going to be 3 times 1 divided by 1,000 times 1 times 10 to the minus 12, and that'll be our answer. So maybe that'll help a little bit. So we're going to write this down. We're going to say we have 3. Well, I might as well put it all in. You don't really have to put the ones, but I'll go ahead and do that. I'll say we have left parenthesis, we have 3 times 1 times 1, right parenthesis, and then I'll say divided by 1, whoops, back 1, divided by 1,000 times, and then I'm going to go 1 times 10 to the minus 12. Second function, double E, negative 12. Whoops, negative 12. We go right parenthesis, and that's what we have here. 3 times 1 times 1 divided by 1,000 times 1 times 10 to the minus 12. We hit enter, and we get 3 to the 9. What do you know? That's exactly what Webassign says, and exactly what we got. And you can do the same thing with picograms and nanograms, and I'm not going to do that for you, so I want to do all your homework for you, and we have a couple more examples I want to show you. So let's see, what else would we say in Webassign here that we would look at? Let's say that we have how many microliters in 3 liters, very similar problem. I'm not going to do that one. Here we go. Express the following number in scientific notation. And so this one reads 9,455, and so you just write 9.455 times e to the plus 3. So it's not anything fancy. Don't put times 10 to the or anything, just e plus 3. This one is 8 times 10 to the minus 5. We know that because we go 8 times 1, 2, 3, 4, 5. We have 20 billion. So we say that we have 2 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You just write 2e plus 10, etc., etc. I think you get it. What else do we have here? Convert the following from scientific to standard notation. Similar stuff. You say 4.68 times 10 to the third. You go 1, 2, 3 over. And same thing here, you scoot over. And this one gives you a couple options here because you don't necessarily have to put a 0 to the left of the decimal, but I like it when you do. And what else do we got here? We have, let's see here. How many significant figures in the following numbers? 1, 2, 3, 4, 5, 6. This one has just 3 because the 0 to the left of an integer doesn't count. This has 3 because they're all integers. 1, 2, 3, 4. This one is 1. And remember, this is 1 or I don't know is the answer, but in computer land, this is just 1 significant figure because integers to the right of zeros to the right of an integer left to an implied decimal point are insignificant in a computer, but left of an actual decimal point are significant. And this is 2 here. So this is all practice for you to get good at this stuff. So this is the same kind of thing. I was hoping to do an operation here for you. Nope. So it doesn't look too bad. Here we go. So let's look at some of these answers here. So carry out the following calculations, expressed each answer in the correct number of significant figures. Well, this is an addition operation, so you follow our rule from earlier, which is to maintain the fewest number of decimal places. This has 3 decimal places. This has 2 decimal places. This has 1, so we maintain 1 decimal place. And same with all these other addition operations. Let's check out some multiplication ones. Here, this one is a multiplication operation, so you keep the same total number of significant figures as there are in the term with the fewest significant figures. So, therefore, you report this one as this has 3, this has 4, so you report 3 significant figures. This has 2, this has 3. We're reporting, now this may be a little suspicious. You say 310, shouldn't I write 3.10 times 10 to the second power? Yeah, you should either way. The computer calls 310 as 2 significant figures. And etc., etc. throughout the rest of this. It's this has 3 significant figures. Here the term with the fewest has 3. Now one hint, in Webassign, all the text you see in red is randomized or measured and is something that always you have to apply significance to. These are random values. Not everybody's homework looks just like this. So that value is generated for each person. So anyway, that's just a hint of how to get into what significant figures are, what scientific notation is, how to use them, how to enter the stuff in Webassign. I hope it helps you a lot, and enjoy.